Welcome to week 12, our final week of class. We're still going to be on the topic of electromagnetic waves, but we're doing something a little bit different this week. Now, what we do in class this week is too late for me to give you a problem set that I could give you the solutions for before I assign you a final, so we can just do something fun. So, what I want to do is to share with you some of the work that I did when I was working on my PhD. Because I worked in a laser lab. That's waves, that's electromagnetic waves. So I want to talk to you about something that's a little bit different from what's within the normal curriculum of electromagnetic waves. And I still think this is fun because, well, a lot of what we do in high school is we're teaching our students the foundations, and they don't know what physicists actually do. So I know we can't spend most of our time in intro classes telling our students about this sort of thing, but if we can squeeze it in here and there, I think it's really fun. And even if you don't, I still think it's good for you as teachers to know what's out there beyond what we can teach in our intro curriculum. Okay, so we've been talking about electromagnetic waves, and last week we were looking at this mathematically. We saw how we can get the wave equation from Maxwell's equation. And then we looked at different forms of the electric field that can be solutions to that equation. So here's the standard picture, which I'm guessing many of you are familiar with. So you have the electric field in one direction, say that's in the y direction, and we have the magnetic field in another direction, say that's the x direction. So they're both oscillating in time and space. And so energy is traveling in the z direction. All right, so we know we have things like wavelength and frequency that all come from this. I thought this week I would spare you my terrible 3D pictures and just go grab some pictures from the internet. So this one's from Noah. So this is the standard picture we teach in intro classes, but it's actually a lot more complicated than that. Well, this is true for a lot of things, but we can make things more interesting. There are other things we can do. One thing that's really interesting is polarization. Let me know if you've learned anything about polarization before. Polarization is something that's really hard to visualize. And back when I was in college, I had to draw myself lots of pictures to figure out what all this text in these books was telling me. But now there's YouTube videos. So I've given you the link here to a YouTube video that is a really nice illustration of polarization. So just take a moment and go watch that other YouTube video because it is a far nicer animation than I could ever produce to go get some idea of what polarization is. And just so you have some idea of what that picture is before you go over there, is it's there's a red wave and there's a blue wave. Those are both electric fields. It's not that one is electric and one is magnetic. They are both electric fields, but one is the x component and one is the y component. So vectors have x components and y components. So it gets a little complicated in waves, right? Because we have a vector in the x direction that varies in time and space, and we have a vector in the y direction that varies in time and space. But the resultant is what you get when you add those two things together. So think of that as the red and blue waves are x and y components, and then it's going to show you a green arrow. That's your resultant. So go watch that video, and then we'll talk about it a little bit more. So in this video, first it shows you linear polarization. So if your x and y components are in phase, that means that the x component and the y component both reach their maximum values at the same place. They both reach their minimum values at the same place. They both cross zero at the same place. When that's going on, you still have linearly polarized light. So you saw that the green arrow stays in the same plane, the resultant vector. But if you change the phase, that means that the red and blue, the x and y components, have their maxima and minima at different times. And what that causes to happen is that it lets the resultant wander around in a circle. So when the x and y components are the same magnitude, when they have the same amplitude, that means it's circular polarization. And if you watch that green arrow, it rotates around in a circle, so that's circularly polarized light. Now, if it's doing this thing where they're out of phase, so their maximum and minimum are different places and their amplitudes are different, then you get elliptically polarized light. So you still have your green arrow going around, rotating, but now it's also changing amplitude and it traces out an ellipse. So go watch that video one more time to see what all these different polarizations are. All right. Well, I hope that made sense. Let me know if it didn't. I'm happy to talk about it lots more in the problem solving discussion. I'm obsessed with polarization. I started working on it for my undergraduate research project. So if you have students going off to college and they're interested in science, please encourage them to find a professor and do undergraduate research. They don't have to wait until they're grad students to do research. So when I was an undergraduate doing research, my project involved changing the polarization of light. There's all these special optics you can use that change the polarization of light. If you use a half wave plate, that's what it's called because it introduces a certain delay between the x and y components that can change which direction of linear polarization. Like you can have it polarized straight up and down, or sideways, or at a diagonal. You can also buy something called a quarter wave plate that introduces a quarter wave delay between the x and y components, and that will make your light elliptically or circularly polarized. So I had a project where I used one of these quarter wave plates and I changed the polarization of my laser, and that made different things happen to molecules. It is really fun. So I've been obsessed with polarization for a long time. So that's one way in which this picture of what an electromagnetic wave looks like can be more complicated. Now, there's another way it can be more complicated, and this is important to what I did in my thesis work as well, is high harmonic generation, is that you can have multiple frequencies of light in an electromagnetic wave. So, the picture on the left is a pretty artist rendering of what high harmonic generation is, that you have lots of different frequencies of light. Now, it's called high harmonic generation. Basically, harmonics means the same thing here it does in music. You have lots of harmonics of the same frequency. We have high because we get up to the 47th harmonic. That's very common that you can get the 47th harmonic of a frequency of light. And that lets you, basically what that lets you do is it lets you make really, really short pulses of light. Like this process can let you make attosecond pulses, which is super cool. Now, the lasers that we use to do high harmonic generation are frequently about 25 femtoseconds long. So, a femtosecond is a millionth of a billionth of a second. An attosecond is a thousandth of a femtosecond long. So, this is all ultra fast. It's really cool. So, this picture on the right is a representation of one of those 25 femtosecond pulses. Well, it's like a 25 femtosecond pulse. This one's a little bit longer than that. So what I want you to notice about this one is it's a laser pulse, and see on the left side, the wavelength is a little bit longer, and on the right side, the wavelength is a little bit shorter. So you actually have multiple frequencies within the same laser pulse. And the red line is the time average intensity. So, all right, so what we've seen is that light is more complicated than this picture. This picture is a great intro, but you can change the directions of your electric field when you look at different polarizations, and you can put more frequencies in at once to make laser pulses. So I want to share with you how this process works. But before I do that, another important point, I show my students this picture on the first day of class. These are all the people I worked with in graduate school. Science is a very social process, and I don't think we communicate that nearly enough. Too many people have the image of just one person working by themselves. This is one of my pet peeves about Big Bang Theory is whenever they show Leonard's lab. You go to his laser lab, there's nobody else there. That is not accurate. You go to a laser lab, there's all these people there. So, see right here, that's Margaret. She was my PhD advisor. And there I am, right there next to her. So these were all other graduate students and postdocs. Oh, right here, this is Henry. He's my other advisor. And so we worked in teams of 3 or 4. We had 4 rooms full of lasers, and it's a big effort. You can't make any of this work by yourself. And I just think it's important for students to know that, because I always worry that people think science is a solo effort, so they think they can't participate in it because they like being social. Scientists are social. Alright, so I want to tell you about how high harmonic generation works. So basically, we have our 25 femtosecond pulse, so that packs a lot of energy into a very short time. So when I focus that laser down onto a molecule, here this is a rendering of a carbon dioxide molecule, it actually rips an electron off of that molecule. And then the electron travels in the laser field, right? Because the laser field is going to make the electron go in this ellipse here. And then the laser field brings the electron back, and the electron recombines with the molecule. That releases a lot of energy. So that creates extreme ultraviolet radiation. Or, depending on your laser and depending on which atom or molecule you are using, you can actually make soft X rays using this process. And the cool thing about this radiation is that it's coherent. And basically, all you need to know about that is that coherent radiation is what you need to make a laser. So, when I talk to elementary school students about this, basically I tell them that I make X ray lasers. Well, I used to. So that's a cool thing to say you're doing. This type of light has applications in making computer chips because the lithography required to make really small computer chips requires extreme ultraviolet radiation, coherent extreme ultraviolet radiation, because that's the only way you can draw really tiny lines etched into those computer chips. So a lot of people that I work with actually go off to work at computer companies for that reason. I was more interested though in studying what molecules do. So when I was in the 10th grade, my chemistry teacher told me that chemical reactions happen so fast we cannot see them happen. This is a challenge to me. I don't know how many people respond this way, but when somebody tells me I can't do something, I want to do it. So basically, because we have such fast laser pulses and we have such a fast process, we can, in theory, see chemical reactions happen using this process. But baby steps. So my project was to see how molecular orientation and molecular vibrations show up in the extreme ultraviolet radiation that we could measure. So I would use one laser to make the molecule vibrate, or I would make the molecule rotate, and then I would see how that looked in our UV radiation, our extreme ultraviolet radiation, because once we could understand how that worked, then the next step would be to look at a chemical reaction and see how that shows up in the signal. Take that, high school chemistry teacher. And then, so this is a schematic of my setup. So the pump laser is a laser that makes the molecules rotate or vibrate. So we focus that into a gas jet of molecules like carbon dioxide or laughing gas N2O or nitrogen, lots of different molecules you can do it in. And then the probe laser, that's the one with a 25 femtosecond laser pulse that makes high harmonic generation happen. So you time delay the probe pulse after the pump pulse. And when you change the time delays between those two pulses, you're looking at different times in what the molecule is doing. Like at one point the molecule is stretched out, another point the molecule is short. So you're looking at the laser at different times by changing the delay between the pump and probe lasers. So this gas jet is a supersonic gas jet. So that means that the gas molecules are moving at a very high speed. But the main point of why we do it that way is that it actually causes the molecules to get really cold. And we want the molecules to be cold so they're moving less. Like when they have, so that they aren't rotating quite as much. Then we have more control over the rotations and vibrations. So then after that, we'd have our pump and probe lasers becoming defocused over here, and we'd have our extreme ultraviolet radiation. That's the blue, that's represented by the blue. So we had a filter to block out the red, and then we just want to look at the extreme ultraviolet radiation. We'd have a spectrometer that's specially made to break up all the frequencies. Because remember I said we're going up to the 47th harmonic. Just think about this in music terms, but instead it's with light. So we have a whole lot of different frequencies in light. Different frequencies give us different information about the molecule. And then we can look at all the different frequencies on my special camera, my Andor CCD, that shows you what each different frequency of light is doing based on what the molecule is doing. So that's my project. Let me know if you have any questions. Let me know if I made sense. I've explained this many times, but I haven't done it in a video before. So I normally get feedback from my audience right away. Anyway, if you have any questions, feel free to ask me. I obviously like to talk about this way too much. Okay, now, I think what students really like to see though is pictures of the lab. So here's me in the lab. I look goofy because my head is tiny, so the laser goggles are too big for my head. We actually had smaller laser goggles, but they didn't fit over my glasses. So, this right here is the chamber where everything happens. So, over here next to me is where we feed in the gas and it goes inside. Inside this clear box is where we have all of our optics to make the laser do what we want. We have our half wave plates, quarter wave plates, polarizers, mirrors, lenses, all sorts of stuff. I spent lots of time playing with that. I always tell people it's like playing with an erector set to have all this stuff in there. It's in a box because air currents actually made the laser beam move enough that it would make our data very noisy if we didn't build boxes. Way back in the room, this tank here is actually full of liquid nitrogen because the crystals that make lasers work get very, very hot when you have laser beams focused on them. So we have to cool them down with liquid nitrogen. And this whole box back here is half the laser. The other half of the laser is back here and it's just as big. Okay, so we bring the laser over here. The gas comes in here. And then we have our filters and such built in here. This little black and gold thing here is the filter that blocks out the red. And the cool thing about that filter, so the filter that lets extreme ultraviolet through and blocks red light is aluminum. It's a very, very thin sheet of aluminum that lets soft X-rays through, but not red. That's cool. And then you go back here, and that's where our camera and everything is. We kept our gases along this back wall over here. So it is fun. I like doing this work, but I got tired of people telling me that they thought physics was too hard or they hated it, so I decided to devote my life to making more people like physics instead of working in my cool lab. Okay, so that's just what I wanted to share with you today. I hope you have found this as much fun as I did. I always like talking about this. I think it's important for people to know what actually happens in physics research because we just don't get to it in high school or the intro classes. Even really most of the classes in undergraduate, you don't get to hear about this. This is something you have to seek out. So I just want everyone to know that this is there. This is just one area of research. There's a lot of cool stuff people can do with physics. It has a lot of industrial applications. We discover a lot of fundamental things. Like when the laser was first invented, people didn't think it had any practical applications. Laser has so many practical applications. It's allowed us to do so much. So even doing fundamental research just for the sake of knowledge often has positive impacts on society. All right. Well, let me know if you have any questions or if you need anything else from me before the final. I really enjoyed getting to know all of you as best I can over discussion boards, and I hope to see you in more of our classes. All right, see you later.